Good afternoon. Today we're going to resume what we have been looking into with polynomial division and continuing on. And we left off with the remainder and factor theorems. And again, for the remainder theorem, if you have a polynomial function f of x, okay, to be divided by a linear binomial expression, okay, that is linear as in first degree, and the binomial we have with x minus c, then the remainder is going to be f of c. And just to give you a little bit of an illustration, okay, now the remainder theorem where you can use this, you could use the determination of the value of a function for a specified input to find out what the remainder is going to be. And let me give you just a case here. Let's say that if you have the polynomial f of x, and we'll just let this be a quadratic function, okay, where we have f of x is equal to x squared plus 5x plus 4 and we'll say this is going to be divided by x plus 2. And in the case of what we have with the divisor, okay, so the divisor, we're going to have it x plus 2. And if we work with the 0 of this divisor, okay, so if x plus 2 is 0, we have x is equal to negative 2. And for this particular polynomial, whenever it is divided by x plus 2, okay, there's going to be a remainder. And the remainder is going to be f of c. And with c at negative 2, okay, the remainder is going to be f of negative 2. Okay. And again, we're using this particular quadratic function. So what I'm going to do here is that for the input variable x, again, I'm going to substitute x with negative 2. And so x squared is going to be the square of negative 2. And we have plus 5x becomes 5 times negative 2. And we have followed by the addition of 4. And we have the square of negative 2 becomes 4. 5 times negative 2, okay, that is going to be negative 10. And we have plus 4. Okay, so you have 4 minus 10 is negative 6. In turn, negative 6 plus 4 is equal to negative 2. And looking at what we have, let's say that in comparison to what we had been looking into earlier. Okay, say we have with synthetic division. Once again, we had x squared plus 5x plus 4. Divided by x plus 2. And looking at it through the lens of utilizing long division in the setup. Not following through with long division, but just setting up in terms of long division. Okay, so you have, let's say you have x plus 2, the divisor. And the polynomial dividend, okay, we have x squared plus 5x plus 4. Okay, and translating the setup, okay, whereupon we can utilize synthetic division. All right. So we have with x plus 2. Again, we have the 0 at negative 2. We have biosynthetic division. Okay, so we got negative 2. And for the coefficients of the dividend, so I have a second degree term, first degree term, and a constant. So there were no missing x terms. Okay, so for the coefficients, I have 1 for 1x squared, 5 for 5x. And again, we have 4 with the constant. And looking at what we have now, okay, so whatever the leading coefficient in the dividend is, okay, that is going to be the leading coefficient in the quotient. So I'm going to bring down to 1, and now we have negative 2 times 1, so negative 2. That's going to be brought over, and then lining up we have 5 plus negative 2. It's going to be a positive 3. And then we have negative 2 times 3 is negative 6. And 4 plus negative 6 is negative 2. And for what we have in the results, we also arrive at the same remainder value of negative 2. And for situations like this, okay, it'll work both ways. Okay, if you notice, okay, we had the remainder from earlier at negative 2 through the remainder theorem and also through the polynomial division. We had the remainder at negative 2, so these are going to be the same each and every time in cases like these. All right, now in crossing over, okay, to what we have in the case of working with a blend of the synthetic division and also application of the remainder theorem, we have from page 280 and our exercise set, and we have for number 35, okay, and here we have a fifth order binomial expression, okay, whereupon we have x to the fifth plus 32 is divided by the binomial x plus 2 and if I look at this through polynomial division, okay, we just go with the log division setup route. And the reason I'm doing the log division setup route, again, is to make sure I'm not missing any terms from the dividend in terms of applying the degrees in the variable x. Okay. All right, so if you notice, we have x to the fifth, and the next and last term we have a 32, so we're skipping quite a few degrees here. Okay, so we're missing a fourth order term. So it's a third order term. We also have missing a square term in x and also a first degree term in x. And again, we close out with the constant. And just, again, putting things in terms of synthetic division. All right, so we have biosynthetic division. Okay, so we have negative 2 for the 0, and placing the coefficients of the dividend. So you have 1 for x to the fifth. And again, we have 4 zeros for the missing terms in x from first order to fourth order. Okay, we have closing out with the constant value of 32. And now taking what we have. Okay, so we have 1 is brought down. Okay, and then we have negative 2 times 1 is negative 2. 0 plus negative 2 is negative 2. Negative 2 times negative 2 is 4. 0 plus 4 is 4. Negative 2 times 4 is negative 8. 0 plus negative 8 is negative 8. Negative 2 times negative 8 is 16. 0 plus 16 is 16. And negative 2 times 16 is negative 32. And 32 and negative 32 with those as additive inverses. Okay, we had the remainder to end up at 0. And I'll just mention this as well. It wasn't asking for the quotient. I just want to mention again, when we looked at 1, this is in reference to x to the 5th. And once this is converted to the leading coefficient of the quotient, we're going down a degree in x. Okay, so this one is now going to be x to the 4th. We have the negative 2 to immediately follow, so this will be in reference to minus 2x cubed. Then we have plus 4x squared. And we have minus 8x. And then we have closing out, we have 16. And I will mention, okay, if I had utilized the remainder theorem, then you have your f of x is at x to the 5th plus 32, okay, and you have divided by x plus 2. Again, for the remainder theorem, okay, so I'm going to be using the 0 of the divisor, x plus 2, just like in the case of synthetic division. And so for the 0, again, we have negative 2. Again, so the remainder we have f of c. And so this will be f of negative 2. And just plugging in negative 2 for x in the dividend. Okay, so you have negative 2 to the 5th plus 32. Negative 2 to the 5th is going to be negative 32. And again, adding 32. So we have additive inverses, okay, to cancel out. And if you notice, okay, once again, we have the remainder with the synthetic division approach. Okay, we landed at 0. Also with the remainder theorem, we had the same result. Okay, remainder is still at 0. All right. Now, for what we have in the case of 36, okay, now we have kind of a similar situation. We have a higher degree polynomial with only 2 terms divided by yet another binomial expression. And for what we have in the case of number 36, okay, so here we have x to the 4th minus 81, okay, and that is all over, let's see, the binomial x plus 3. Now if we look at this through polynomial division, okay, so in terms of the setup, okay, so we have x plus 3 is the divisor, And for x to the fourth, minus 81. Okay, so we're going to have some missing degree terms. So we have a missing third order term, a missing second order term, and a missing first order term. Again, we have minus 81. And translating in the context of synthetic division. Okay, so if I take the 0 of x plus 3, okay, so we have negative 3. And we have by synthetic division. Okay, so we've got negative 3. Again, the 0 is isolated, and for the coefficients of the dividend, so I have 1, 0, 0, and 0 for the missing x terms from first to third degree. Again, we have closing out with the constant value, negative 81. Okay, so starting out with 1, okay, so bring this down, negative 3 times 1 is negative 3. 0 plus negative 3 is minus 3. And we have negative 3 times negative 3. Okay, so that is going to be 9. 0 plus 9 is 9. Negative 3 times 9 is negative 27. 0 plus negative 27, having minus 27. And the product of negative 3 and negative 27. Okay, so that'll be positive 81. And negative and positive 81 will add up to 0. Okay, so you have the remainder is equal to 0. And just to recap, okay, so you have with the remainder theorem, okay, so you have divided by x plus 3. And again, in the case of the remainder theorem, so I'm going to take the 0 of x plus 3 again. So just like in the case of the synthetic division, we have negative 3, okay, in lieu of the binomial x plus 3. So you have the remainder is equal to f of c. And again, that's going to be f of negative 3. And just plugging in directly. Okay, so you're going to have negative 3 to the fourth minus 81. And negative 3 to the fourth, again, negative 3 times itself, times itself, times itself. So that will be at 81. And this also comes out to 0. So you can see you have that bit of history to repeat. Okay, where we had the remainder to be at 0. Okay. And in some cases now, for numbers 35 and 36, it looks like the remainder theorem approach is a faster way to get to the remainder in comparison to the polynomial division. And one might wonder if that is always going to be the case. And I would say not necessarily. It just depends upon the nature of the dividend. In this case, we had only 2 terms, so just with the 0 I was able to plug in for f of x. But if you have like a long polynomial dividend, especially with higher absolute value coefficients, I would say synthetic division would probably be your preferred route in terms of finding out what the remainder will be. And now for what we have for the next set of items, and we have regarding what we have for the remainder theorem. Okay, and this is going to be a bit of a change up. And lines here. Okay, so we got with number 41. Okay. So you have a polynomial f of x. And we have is equal to 2x to the fourth minus 5x cubed, and we have plus x squared minus 7. Okay, and you have is divided by the binomial x minus 4. All right. And in both cases now we're looking at the determination of the remainder. Right. And for what we have in part A, so you have by the remainder theorem, okay. Okay, so this is the dividend, okay, we're working with, okay, and for the divisor, okay, so you have x minus 4 is equal to 0, and we have x is equal to 4, and in the remainder theorem, okay, so your c value is going to be the 0x value, which is going to be at 4. And so for what we have in the case of part A, here, f of x is going to translate to f of 4. Okay, so 2 times 4 to the fourth minus 5 times 4 to the third. And we have plus 4 squared minus 7. And just filling in. Okay, so 4 to the fourth. So this will be at 256. We got minus 5 times the cube of 4. 4 cubed is going to be 64. We have 4 squared is 16. Again, we have followed by the subtraction of 7. And here we have in following through, so you got 512. Negative 5 times 64 is going to be a negative 320. And we got 16 minus 7. We can go ahead and put these together. So we have a plus 9. And so we got 512 minus 320. So that'll be 192 plus 9. And so we have for that result, okay, this will come out to 201. And again, we have in terms of polynomial division. Okay, and so again we have this particular polynomial. Okay. And the divisor, again, we have x minus 4. Okay, so we have into 2x to the fourth minus 5x cubed. Okay, we have a second order term. And we're missing a first order x term. And we have closing out with negative 7. And through the synthetic division, okay, so you got 4 for the 0. And for the coefficients, now we got 2 and x to the fourth. Negative 5 is the coefficient of the cubic term. 1 for the coefficient of the square and x term. Again, we have a void in the first order in x. And again, we have closing out with -7. Okay, so again, the leading coefficient we have from the dividend is going to be at 2, which will be that which we have in the quotient. So after bringing 2 down, we have 4 times 2 is 8. Part is brought over into the next column, and adding, we have -5 plus 8, so that will be 3. Then we have 4 times 3 is 12. 1 plus 12 is 13. 4 times 13 is 52. And we have 0 plus 52 is going to make 52. And we have 4 times 52. Okay, that is going to be 208. And -7 plus 208, okay, it's going to yield the last column total. And again, the remainder, okay, is also equal to 201. Okay, so regardless of whether you utilize the remainder theorem or the synthetic division, okay, you're going to come out to the same remainder value. And okay, just for what we have in similar fashion, okay, now we got with number 42. Okay, so you got g of x, and here, okay, we're going to have this set equal to 3x to the 5th. Then we have plus, okay, 2x to the 4th. And then we have plus 6x squared. And we have minus x plus 4. Again, this is going to be divided by x minus 2. All right. So once again, in the case of part A, okay, again, by the remainder theorem, so again, this is our dividend. And in the case of the divisor, okay, so we have x minus 2 is equal to 0. If x equal to 2, which is going to be the pertain to c value. Okay, so in case of the polynomial g of x, now the remainder, whenever this 5th order expression is divided by x minus 2. Okay, so this is going to be g of 2. Okay, so I have 3 times 2 to the 5th. Yeah, plus 2 times 2 to the 4th. We have plus 6 times 2 squared. And we have minus x, this will be minus 2. We have plus 4. And after substitute, so 2 to the 5th is going to make 32. We got 2 times. Now 2 to the 4th is 16. We got 6 times. And 2 squared is 4. And we just go ahead and put together -2 and 4. So that will come out to a plus 2 at the end. And following through, so we got 96. Then we have plus 32. 6 times 4 is 24. We got plus 2. And for what we have in this particular case, right, before I get too far ahead, my eyes are playing tricks on me. No damage done though. Got -3x to the 5th. Let's see, you double check here, minus 2. Yeah, so just double checking. So got negative 96. Yep, make sure I got this right. So got negative 3x to the 5th, 2x to the 4th, 6x squared, minus x plus 4. Yeah. So you got negative 96 plus 32. Okay, so that would be negative 64. Negative 64 plus 24 is negative 40 plus 2, so that will come out to negative 38. Okay. Now, for what we have in the case part B, and what I'll do here, okay, just kind of bypassing the long division setup. So I want to mention, okay, so you got, okay, you have this given polynomial, g of x, okay, and to be able to set this up in terms of synthetic division, again, we want to place emphasis on making sure that all the degrees, okay, down to the constant will be covered. Okay, so you got g of x, so you have x to the 5th, x to the 4th. Notice we have a cubic term that is missing. So use 0 for placeholder purposes, and got x squared, first order x, and we have a constant. And again, okay, by synthetic division. Okay, so we're looking at this same binomial expression. Okay, so with the synthetic division, so I'm taking the 0 out of the divisor. Okay, so you have it negative 2, positive 2. Trying to get my negatives and positives right. Okay, so you got x minus 2 equal to 0, so you have 2 is the 0. And let's see, so you got negative over here. We'll make sure I've got this set up. Yep, so you got negative 3. Okay, so looking at what we have now, so we got negative 3 for x to the 5th, 2 for x to the 4th, 0 for the cubic term, 6 for the square, negative 1 for negative x, and we have 4 at the end. Okay, so just taking what we have now with the synthetic division. Okay, so we got negative 3, and 2 times negative 3 is negative 6. 2 plus negative 6 is negative 4. 2 times negative 4 is negative 8. 0 plus negative 8 is negative 8. 2 times negative 8 is negative 16. And 6 plus negative 16. Okay, so that'll be negative 10. And 2 times negative 10, that will be negative 20. And negative 1 plus negative 20, so this will be negative 21. And we have, for the last part, we have 2 times negative 21, which would be negative 42, and 4 minus 42. Okay, so this will come out to a negative 38. Okay, and so you have that bit of history to repeat from whether you are using the remainder theorem or synthetic division, you come out to the same remainder result with minus 38. Yeah, so it works in both cases, and just make sure you copy down the problem properly, okay, as I had failed to do so earlier. Okay, now for what we have in the case of next round, we're throwing in, okay, along with the remainder theorem, the use of the factor theorem. And for what we have in the case of 48, okay, so we got g of x, okay, and we have equal to 2x to the fourth, and then we have plus 13x cubed, and we have minus 10x squared, we have minus 19x, we have plus 14, okay, and we have posed the question, okay, is c is equal to negative 2, a 0? And another way of asking this, okay, is going to be, is x plus 2 a factor of g of x? And okay, now if we go with, say, the remainder theorem, you could also do the synthetic division as well. But for the, say if I go with part 8 utilizing the remainder theorem, okay, so the remainder, okay, we have again g of c, and c is already spelled out as negative 2 and looking at filling in negative 2 for x in the expression. Okay, so we got so 2 times negative 2 to the fourth. Yeah, plus 13 times 2 to the third, minus 10 times negative 2 squared, minus 19 times negative 2, and we have followed by the addition of 14. So after filling in negative 2 in place of x, so we have 2 times 16, and we have plus 13 times negative 8, we have minus 10, and we have the square of negative 2 is going to be 4, and we have negative 19 times negative 2, so this will be positive 38, and plus 14, and 2 times 16 is 32, 13 times negative 8 is negative 104, negative 10 times 4 is negative 40. Now 38 and 14 will both add up to 52. Okay. And so for the remainder here, we got 32 minus 104, that's a negative 72, minus 40 is negative 112, plus 52. So the result, okay, is going to be at negative 60. Okay, and so for the remainder, okay, that is negative 60. And since the remainder does not equal to 0, it's going to follow that by the factor theorem. Okay. Going back to our yes or no question. In terms of whether x plus 2 is a factor of g of x, or more succinctly, whether negative 2 is going to be a 0, and the answer to that question is going to be a resounding no. Right. Now, for what we have in the case of part B, Okay, we're now dealing with whether c equals -7 is going to be a 0. Another way of phrasing this, okay, is going to be if x plus 7 is going to be a factor. Okay. So again, this is our g of x. Alright, and if you notice, okay, we've got fourth order, third order, second order, first order, and constant terms. And so what you could use the remainder theorem again, but if I go with synthetic division, okay, so I already have -7 as a 0 of the divisor, but in terms of whether it's going to be a 0 of this polynomial, I can line things up here. So I got -7 as a 0 of the divisor. Now for the dividend, so I got 2 for x to the 4th, 13 for x cubed, -10 for x squared, -19 for x, and then we have 14 for the constant. And setting things up here, okay, so if I bring down the 2, now we got -7 times 2 is -14. 13 plus -14 is -1. And we got -7 times -1 is a +7. -10 plus 7, we have a -3. Now -7 times -3 is going to be a +21. -19 plus 21, okay, that is going to be 2. -7 times 2 is -14, and 14 minus 14, okay, that is equal to 0. So for what we're going to have here, okay, so got your remainder, regardless of whether you use synthetic division or the remainder theorem. You got your g of c is going to be g of -7, and that is going to be equal to 0. Okay, and so in terms of whether c equals -7 is going to be a 0, well, since the remainder does test out to equaling 0, the answer to part B is going to be yes. All right, and had I used the remainder theorem, okay, the result, okay, like in this case, if I literally plugged in -7 for x, g of -7 would be equal to 0, and that would be a case of where using the remainder theorem follow through or determining the function value will be a painstaking exercise in comparison to the synthetic division. Now, looking at taking what we have with zeros. Okay, now we looked at forming polynomials from, say, given zeros and multiplicities, and now in the realm of polynomial division, okay, there's going to be sort of a parallel to this, and instead of forming polynomials, we'll be looking at factoring polynomials on the basis of given zero values. And we have for this part, okay, so we got determining factors of polynomials. From given zeros. Okay, let's give you a couple of cases here. If you're looking at factoring, oops. Okay, so if you're looking at factoring, okay, we have trinomial expression. Let's say we have f of x is equal to 2x squared minus 6x plus 4 given that 2 is a 0. All right, and we can determine the factorization case. So if I look at taking what I have through synthetic division case, you have 2 is going to be the 0. And double checking, okay, so we have for the dividend have a square term, a first order term, and a constant. Okay, so if I place the coefficients, so you got 2 for x squared, negative 6 for the first order x, and again we have the constant value 4. Now mention, okay, if the given amount is a 0, then the remainder after the synthetic division should also be at 0. Okay, and following through, okay, so you have leading coefficient from the dividend is 2, and this will be brought down. Okay, and then we have 2 times 2 is 4. Negative 6 plus 4 is negative 2, and 2 times negative 2 is negative 4. And 4 plus negative 4 is 0. So again, just to restate, okay, that is going to be the remainder. Okay. But now for the items of interest, okay, so 2 is a 0. And so for the divisor, what divisor does that represent? Well, think of it kind of like working backwards. You say that, in other words, backwards from the zero product property. Say like if x is equal to 2, this will come from having set equal to 0, the binomial x minus 2. Now for the quotient, okay, so I have 2 and negative 2, so the 2 from the dividend was in reference to 2x squared. And after the round synthetic division, okay, the leading 2 now is going to be in reference to 2x. We have the constant negative 2 to follow. And just for the factorization, okay, so what I have here, maybe there's to show up. Yeah. So you got f of x is equal to 2x squared minus 6x plus 4. Okay, and for the initial setup, you're looking at the product of the quotient and the divisor. And sometimes the product of the quotient and the divisor, okay, will be the final factorization. There can be times when you can factor out even further. And from the quotient, we've got 2x minus 2. And this can be factored out even further since we have a common factor with 2. And so we have 2 times the quantity of x minus 1 times that of x minus 2. And let's say if we have in the case of factoring, okay, so you have a cubic polynomial. Okay, you have 4x cubed minus 20x squared. So we have plus 33x minus 18. And so we have given that 2 is a 0. Once again, so I had 2 as a 0 in the first case, and we'll use it again in the second. Okay, so if I were to utilize synthetic division, so just to double check, okay, make sure that there is not a missing degree term from the dividend. So got a cube, a square, a first order, and a constant. Okay, so we're good to go. Okay, so we have lining up the coefficients for the synthetic division process. Okay. Okay, so the 4 is going to be brought down. Okay, now we got 2 times 4 is 8. Negative 20 plus 8 is negative 12. And we have 2 times negative 12 is negative 24. 33 and negative 24 is going to be 9. And 2 times 9 is 18. Negative 18 plus 8 is 0. Okay. And a 2 again is a 0. The remainder again should be at 0. And once again, we have from 2, we got the divisor at x minus 2. Now for the quotient that we have here, and this is one that can be lowered ultimately, but for now, okay, leading 4 here, again, we're transitioning from 4x cubed to 4x squared. We've got minus 12x. And we have followed by 9. Okay, so in the case of this particular polynomial, okay, so we got the quotient with 4x squared minus 12x plus 9. We have times the quantity, once again, of x minus 2. Again, adopted from the given 0 value at 2. And I can take this even further. Okay, so we got with 4x squared minus 12x plus 9. Now this trinomial can be factored to 2x minus 3 times itself. Kind of like establishing from factoring by grouping. And again, just condensing. Okay, notice we have a repeating factor with 2x minus 3. Okay, and just kind of like how Alex might want it. Okay, so having the factor to show up as repeating, I'm just going to apply raised exponents. Okay, so 2x minus 3 times itself, that is going to be the square of 2x minus 3, and then we have times the quantity of x minus 2. So that will be the complete factorization of this particular third order polynomial expression. Okay. And Tell you what, just for the next few moments, okay, tell you what, let's see what we get in the case of factoring. And in this one, okay, just the quotient times the divisor will be the complete factorization. And let's see what we get for f of x is equal to, we'll say we have 3x cubed minus 41x minus 28, and we have given that 4 is a 0. Okay, so we have one factor is going to be x minus 4 from the given 0 value of 4. Okay, so let's see what we get in factoring out 3x cubed minus 41x minus 28. Okay, let's looking at what we have for the dividend. Okay, and all right, so we have given that f of x is equal to 3x cubed minus 41x minus 28. And if we were to look at utilizing synthetic division, okay, so we have an x to the third, okay, and if you notice, you had to jump all the way to minus 41x. Okay, so we have a missing second degree term. Okay, so if I were to explicitly have all the degrees labeled from the order of the polynomial to the constant, so we're going to have the 0 placeholder for x squared, then we have negative 41x and minus 28, and we have given that 4 is a 0. So again, utilizing synthetic division, so 4 is a given 0. Again, for the coefficients of the polynomial dividend, so you got 3 for x cubed. Again, we have the placeholder 0, signifying that a squared term is missing. We've got minus 41 for the x, and negative 28 again for the constant. Okay, and so looking at what we have in the process. Okay, so leading coefficient 3 is going to be brought down. Now we've got 4 times 3 is 12. 0 plus 12 is 12. 4 times 12 is 48. Negative 41 plus 48 is 7. And then we have 4 times 7 is 28. And negative 28 plus 28, okay, that is 0, which we do want. Okay. So we got the remainder is 0. Okay, and in terms of the divisor and the quotient, okay, so you have like if x equals 4 is a 0, you say that the 0 stems from the factor x minus 4. Okay, so you have the divisor x minus 4, and in terms of what we have for the quotient. Okay, so I'm going from 3x cubed to 3x squared. And then with the 12 and the 7, we'll have plus 12x plus 7. And so we have in the follow through. Okay, so I got 3x cubed minus 41x minus 28. And for the factorization, okay, we got the quotient. Okay, so we have 3x squared plus 12x plus 7. We have times the quantity of x minus 4. And this will be the complete factorization. And the reason I know this is that if you were to think along the lines of factoring by grouping, again, you had the first and last coefficients of the quotient. Okay, we'll have a product of 21. And there are no integer factors of 21 that will add up to 12. You think of 3 and 7, which will be 10. And the only other combination will be in the positives. You have 1 and 21, and they will add up to 22. So there's no combination that will add up to positive 12. So in this capacity, you have just the quotient times the divisor will be the complete factorization. Okay, and so far, okay, we've had working with polynomials in direct terms, and now looking at rational functions. And we, time and again, and even going back to chapter R, we've had stuff like restricted values, and there's going to be a bit of a return to this. And for what we have in this case, I'm just going to give a bit of a brief intro to asymptotes, or at least vertical asymptotes.
Can you spell that A word?
Okay, asymptotes, A-S-Y-M-P-T-O-T-E-S. Think of like A-S-Y-M-P, and then totes as in totes umbrella.
Thank you.
Uh-huh. I used to work in retail, and I saw these umbrellas from time to time, and it was like the totes brand. I think it also had like other accessories like caps and that sort of stuff. Okay, now for domain and vertical asymptotes of rational functions. Okay, and say we have a rational function r of x. Well, stay still. Okay, so we have for a rational function r of x. Okay, now in the case of the domain, again, now the rational function could be in the form of f of x, g of x, z of x. I'm going to put this in the context of uppercase r of x. And for the domain, again, nothing new here. You're going to have the set of all x values. You have the set of all x values, okay, where r of x is defined in the set of all real numbers. Now for what we have in the case of vertical asymptotes, okay, now a vertical asymptote, okay, that is going to be a vertical boundary that is going to split Okay, so I have a vertical boundary that splits the graph of R of x. And in terms of its origins, it's going to be formed by exclusions from the domain. Whose factors remain and I'll put emphasis on this. Again, this is going to be after R of x is reduced to lowest terms. And I'll give you just a case here. Okay, let's say if I determine the domain and vertical asymptotes so we have R of x is equal to x squared minus 1 all over x squared plus 3x plus 2. Okay, so we have at least in the procedure. Okay. Again, whenever you're looking for domain, you're looking at the restricted values before any simplifying is done. Okay, so we have for the restriction now for a fraction, we cannot have a zero-valued denominator. Okay, so for x squared plus 3x plus 2, this cannot be 0. So we cannot have the factors of x plus 2 and x plus 1 to be 0. So if x plus 2 and x plus 1 cannot be 0, that means we're going to have a couple of values excluded from the domain. So we're going to have the x cannot be negative 2 and the x cannot be equal to negative 1. Okay, so we're going to have for the domain okay, so you're going to have those values of x that would be less than negative 2. Negative 2 is going to be bypassed, and we have those values going past negative 2 and approaching but not including negative 1 And we have for the rest, you have those values of x which will be greater than -1. Okay, so that is going to be the domain. Now, for what we have in the case of the asymptotes, okay, so for x squared minus 1 over x squared plus 3x plus 2, again, the numerator is going to have a difference of squares. And the denominator, again, this will factor out to x plus 2 and x plus 1. Okay, and I'm duplicating this, and there is a reason for this. Okay, if you notice, you have a common factor between x plus 1 at the top and bottom, so these are going to go out. And for the completely reduced form, okay, so you're going to have x minus 1 all over x plus 2. Okay, and I'm just going to mention now, x plus 1 cancels. Any zero that has a corresponding factor to completely cancel, this is going to signify, okay, I'm just going to put here, cancels completely. Any zero that has a corresponding factor to cancel completely. Okay, this is going to be a hole in the graph. So x equals -1 is a hole, like a discontinuity point. And now for x plus 2, our other denominator factor, okay, we have x plus 2 remains after complete simplifying. X plus 2 remains, and any denominator factor that remains after simplifying, the corresponding zero is going to be the vertical asymptote. I'm using VA for vertical asymptote. And just for what we have, at least in the overall picture, okay, and you have just your values of interest. So you got -2, -1. So there's a vertical asymptote at x equal to -2, and again, and this is going to split up the graph of our rational function. And just for the nature of it, again, just doing a bit of a rough sketch here. And let me mention now, the graph of r of x never comes into contact with the graph or the vertical asymptote. Okay, and so for what we're going to have in this particular case, all right, so we have again, I'm not drawing this according to scale. I wanted to signify. Okay, so at x equals -1, we're going to have a discontinuity point. And we have a hole at x equal to -1, and these blue curves will be in reference to the one and same function which we have with x squared minus 1 all over x squared plus 3x plus 2.